Right, our next speaker is Yunchao Liu from UC Berkeley, currently a PhD student, and he's been doing some very interesting work in establishing theoretical foundations for near-term quantum advantage, which I believe he's going to tell us about today. So.
Test. Hello, everyone. It's my pleasure to be here to talk about the complexity and applications of random circuit sampling. So in 2019, Google claimed a quantum breakthrough that would change computing. This experiment is called random circuit sampling, which has three components. First, we use current noisy intermediate scale quantum devices to sample from a random quantum circuit. And second, we use a statistical test to evaluate how good the device is performing. And third, we claim that the same performance cannot be achieved classically. So these experiments represent a great advance in physics experiments. And from the CS perspective, it represents a great advance in exploring the high complexity regime of quantum mechanics. So here's what the experiment is about. Google performed random circuit sampling on 53 qubits with circuit depths up to 20, and the device has roughly 1% noise per gate. So after collecting M samples from a device, we compute this statistical measure called XEB, which is basically a linear function of the ideal probability of the random circuit from these samples. So roughly speaking, this statistical measure is a score between 0 and 1, where 0 means we are doing trivial uniform sampling, and 1 means perfect sampling from the ideal RCS. And due to noise, experimentally, a score of 0.002 is achieved. So last year, Pan, Chen, and Zhang developed a brute force tensor network algorithm to achieve the same task using 500 GPUs in 15 hours. However, this is not really the end of story because this algorithm runs in exponential time and it's unlikely to be practical with larger system size. So what is going on here is that there is an exciting race between classical and quantum. So since 2019, there has been larger RCS experiments up to 60 qubits. And in particular, this algorithm already struggles with this larger system size. So the central question here is, will there be new spoofing algorithms for larger experiments? So today, we will take a step back from this exciting race, and we will ask a more fundamental question, which is there convincing evidence from complexity theory showing that noisy RCS experiments are inherently hard for classical computers? So in part one, we will report recent progress to address this question 3 years after the experiment. And in part two, we will show a practical application of RCS in quantum benchmarking. So there are multiple approaches to show evidence of high complexity in RCS. We will only focus on the noisy regime, which is directly relevant to show that even the tiny XEB achieved in recent experiments is hard to achieve classically. In 2019, Aronson and Gunn formulated a conjecture called X-quads, which says that even a tiny correlation of order 1/2 to the n with the ideal RCS distribution is hard to achieve classically. The reason that they had to formulate this strong conjecture is because this was necessary for them to support the hardness of tiny XEB experiments. So this has been a very reasonable conjecture since 2019, and therefore it provides the complexity evidence that we needed. However, last year, recent work of Gao et al. Cast doubt on these arguments. This sort of reopens the question, is there high complexity in noisy RCS experiments? So this is the main result from my recent paper called A Polynomial Time Classical Algorithm for Noisy Random Circuit Sampling. So what we show is the following. We take an RCS experiment which produces M samples. And then we give a classical algorithm that can also produce M samples, which takes Pauli M time. This could be longer than the experiment, but not exponentially longer. So these samples comes from a distribution that is so close to the experimental distribution such that no statistical test can tell the difference between the two. So here is the technical statement of the algorithm. Basically, it's a simple corollary from this statement, which says that we can achieve small total variation distance. Yeah. So okay. So basically, this algorithm can achieve any specific specified total variation distance. And then given number of samples m, we just choose the desired error to be roughly 1 over m, and then that guarantees indistinguishability. Okay. So what happens here is that the running time of our algorithm is at most a polynomial in the running time of the experiment in order to be indistinguishable from the experiment. So an important remark here is that currently the running time of this algorithm is not practical. It has running time roughly m to the power of 1 over gamma, where gamma is the noise per gate. So do we care about polynomial time algorithms if it's not practical? The importance of polynomial time comes from the question of understanding if RCS is an asymptotic experimental violation of the extended Church-Turing thesis, which is a very fundamental concept in complexity theory, saying that whether a model of computation can be simulated classically in polynomial time. So the above result give a negative answer to this question. Of course, the result has some conditions that I'm happy to discuss if it comes up. Okay. So next, we will have a slightly more technical discussion about the role of circuit depths. So as we see previously already in the numerics, due to noise, the output distribution of a noisy RCS experiment is very close to uniform. In fact, it is exponentially small in circuit depths. And therefore, experimentally, in order to see anything non-trivial, we need to collect at least 2 to the d samples. This means that in general, both the experiment and our algorithm have running time exponentially in d. This means that using a large circuit depth is not practical for both the experiment and our algorithm. However, there is a particularly interesting regime of log n depths that was known as the sweet spot for scalable quantum supremacy, because in this regime, everything is fully scalable, and both the experiment and our algorithm now have polynomial running time in the number of qubits. So next, we give a brief sketch of where our result comes from. The intuition of the prior work of Ahrens and Gunn is to consider this very simple idea of Feynman path integral. So basically, if we look at this equation, we notice that the right-hand side is the sum of many, many terms, 2 to the nd many terms. And if we have a classical algorithm, we can just only sum over polynomially such random paths. And this only gets exponentially small correlation with the distribution. And therefore, they conjecture that no classical algorithm can achieve better than 1 over 2 to the n correlation. This seems very reasonable. And in fact, our classical algorithm is actually based on the same idea, which shouldn't work, but somehow now it works if we consider different bases. So what we do is to consider the path integral in the Pauli basis, which we call Pauli path integral. And the algorithm has 2 main ideas. The first main idea is that in the Pauli basis, the paths are highly non-uniform, unlike in the computational basis. And this is related to this remark saying that due to noise, the contribution of a given Pauli path decays exponentially with the number of non-identity Paulis in the path. And therefore, we can order the different paths by importance and only consider the most important ones in our simulation algorithm. And the second idea is to design an efficient algorithm that actually can calculate all of those important paths to achieve the desired error. And the algorithm actually uses this unitarity constraint that was highlighted in the yellow, saying that actually not all paths are possible, only those ones that obey the constraint of mapping identity to only identity is non-trivial. Okay, so that's all for the algorithm. So here is a brief discussion. So we know that RCS is an exciting experiment with multiple aspects. First, it's a very powerful method for benchmarking quantum devices, which we will see next. And second, we know that the current exciting back and forth with classical spoofing strategies inspire the continued improvement of quantum devices. So this is a very good news for our field. There are some issues also with scaling up RCS. The first is that theoretically, we give strong negative evidence for RCS as a scalable experimental violation of the extended Church-Turing thesis. And there is a much more practical issue of it's much harder to perform verification as the system gets bigger. Overall, this seems to be a very exciting time to start developing new proposals for near-term quantum computational advantage with a better complexity foundation. And the particularly interesting idea is the cryptographic proof of quantumness protocols, which has a solid complexity foundation, is verifiable. The only issue is whether it can be implemented on near-term quantum computers. And currently, Umesh and the co-authors are doing the resource estimation for these protocols. So next, we will move to the benchmarking. Any questions?
Yeah, it's a very nice paper, which I really enjoy reading. I guess I will put it in a different way. I would say, you know, if you keep noise constant as you scale up, then you're exponentially approaching the uniform distribution, and they see that for random gates, and then your algorithm, you know, works because it just produces uniform samples. But what I think is the most interesting is that the feature that you say in passive, you know, scales with 1 over the noise. I think that's kind of fundamental. I mean, what you're showing again is that in the low noise regime, you're actually, you know, as long as the noise per cycle is less than 1, then the algorithm is exponential. But once you get into the high noise regime, then you sort of lose, you know, the random circuit sampling. I mean, you're converting to uniformity, and then it becomes, you know, sample uniform distribution. I guess maybe you agree with that. I guess my main thing I'm trying to say is that when you say correlated time is not practical, I think that's fundamental.
Yeah, I agree. So I have two remarks. The first remark is that from the theoretical perspective, there is still some chance that we can significantly improve this running time. So that is totally a bit unclear. But I agree with that. Practically speaking, if we do have very, very small noise per gate, then we do not expect a practical algorithm to exist for RCS.
What I like about your paper is that it's, you know, qualitative properties, right? What you need is noise per gate, which is less than inverse number of qubits.
Yeah.
Yeah. You know, which you also find another way. Yeah. And I think that's fundamental. I guess that's what I'm saying. I don't think it's, you know, like a practical feature. I think that's fundamental. So.
Yeah, I agree with what you said.
Thanks.
Okay. So next we will discuss applications of RCS in benchmarking. So by benchmarking, what we mean is to design algorithms to learn about noise in quantum devices. So here is the central challenge in benchmarking, which is how to deal with crosstalk and correlated errors. So in particular, here's a simple noise model. On the left-hand side, we have two independent errors on two different gates. Each happens independently with probability 1%. On the right-hand side, we have one error that happens on both gates with probability 1%. So basically, the goal is to distinguish between the two cases. So using the standard technique called randomized benchmarking, which can estimate the marginal error on individual gates, it doesn't do the job because it will just output 1% on each gate in both cases. However, a simple way to solve this problem is to find a way to estimate the total error on this layer of gates. And in this case, the left-hand side has total error 2%, and the right-hand side has total error 1%. So next, we will actually discuss an algorithm for estimating the total error in a layer of non-Clifford gates. So interestingly, this has been an open challenge in the field of benchmarking because the standard techniques that we use for benchmarking, like these type of circuits, only works for Clifford gates. Interestingly, we show that basically using RCS, we can solve this problem. And interestingly, it works for any 2-qubit gates, regardless of Clifford or non-Clifford. So of course, the motivation of this algorithm comes from Google's experiments. So in Google's experiments, XCB was also used as a proxy of the fidelity of their experiment, which will come back later. And if we look at the paper, besides quantum supremacy, there is also this very interesting claim that the noise in their device was uncorrelated. So this is very interesting because we have just seen that distinguishing between correlated and uncorrelated noise is a very challenging task from the perspective of benchmarking. So Google's claim must mean that there is something interesting in the experiment for benchmarking. Okay, so here's what this claim is about. In this figure, we can see two types of data. So the data points, as shown by the circles and crosses, they represent the XCB of the experiment, which we can also understood as the fidelity. And then there is the black line, which is called digital error model, which is a simple formula by simply multiplying individual gate fidelities. So here we call this FRB because these individual errors come from the standard randomized benchmarking experiment. So the spirit behind this equation is the independence. So we know that for independent events, the joint probability is the probability of each individual events. So here is one way to think about what's going on in this experiment. Maybe the errors in the device is uncorrelated. In this case, we can curiously argue that the fidelity should equal to the probability of no error, which would be, by independence, be the product of the probability of no error on each gate. So let's plot both things. The XCB is a proxy for fidelity, and then we can also plot this digital error model, this simple product equation. If they agree with each other, this suggests that the hypothesis that the noise in the device was uncorrelated is correct, which would be great news because this is good news for fault tolerance. Okay, so there are two things happening here. First, we have the observation that the XCB agrees with the digital error model in the experiment. And second, we have the claim that this coincidence in the experiment data indicated that the noise in Google's device is actually uncorrelated across each 2-bit gate. So basically, a natural question is, can we understand this observation from a theoretical perspective? And more generally, could this observation be the hint of a multi-qubit noise benchmarking algorithm for non-Clifford gates? So we answer both questions positively. We show that the XCB in the experiment scales roughly as e to the minus t times d, where t is the total amount of noise in an arbitrarily correlated noise model acting on each layer of gates. And therefore, we can use XCB to learn the value of t. And as a corollary, we show that if the noise model was highly correlated, then XCB would deviate from the digital error model. And this gives evidence that supports Google's claim. So here's some more details regarding this result. Let's consider arbitrary Pauli noise channel, which is just a distribution acting on all of the Pauli operators. And we want to estimate the total error, which is the sum of all of the errors that are not all identity. So here, we assume the total error is small, meaning that this is not a scalable argument. We just want to benchmark dozens of qubits. And what we show is theoretical evidence for the exponential decay of average fidelity for random quantum circuits. Fidelity just means the inner product between the ideal quantum state and the mixed state generated by the experiments. So experimentally, we actually estimate fidelity using the XCB. And this is because fidelity itself is hard to estimate. It takes exponentially many samples. And therefore, we use XCB as a sample efficient proxy. So now this algorithm is very clear. We just sample a bunch of random circuits at different depths. And then we estimate XCB of each circuit. And then we fit an exponential decay function and obtain the value of D, where we use XCB as a proxy for fidelity in the second step. Okay, so now it's time to go back to the original problem of understanding what's going on in this observation that claims uncorrelated noise. So for this, we can go back to the previous toy model. So in this toy model, basically there is an uncorrelated and a correlated noise model. So let's think about what happens with XCB and the digital error model. So on the left-hand side, the total error is 2%, and therefore XCB decays at a rate of 2%. And of course, both individual gates have error 1%. So overall, the digital error model FRB will also decay with a rate of 2%. On the right-hand side, the total error is actually only 1%. And therefore, XCB will only decay with 1%. Meanwhile, because the digital error model doesn't distinguish between local and correlated noise, it still decays at a rate of 2%. To see that, we can heuristically simulate a highly correlated noise model and basically clearly see the difference. So in this case, the FRB will decay much, much faster than XCB and fidelity. So a one-sentence summary to this result is that total error approximately equals the sum of marginal errors, implies low correlated error. And this is exactly what's going on in this experiment. Okay, so here's the conclusion of the talk. So first of all, to achieve larger speedups, RCS and quantum supremacy experiments motivate the development of larger and better quantum devices. And here, the accumulated experimental advances and the theoretical understanding in complexity theory provides the foundation for the next challenge problem for future devices. And second, RCS provides a powerful technique to benchmark quantum devices, such as estimating the total amount of noise on a layer of non-cleaver 2-qubit gates. And this allows us to provide formal evidence to support Google's claim that the noise in their device was uncorrelated. So that's all. Thank you.
What extent could this Pauli process will be used to sample arbitrary circuits? To what extent is it unique to random circuit sampling?
Yeah, great question. So roughly speaking, randomness is crucial for our result because we want to be able to claim that if we compute enough Pauli paths, then the total variation distance is small. That statement for now only works with randomness in the circuit.
Sample complexity and computational complexity of the estimator and benchmarking.
Yeah. So as I said, basically we want to use XEV because it's sample efficient. So for each circuit, if we want to estimate with the epsilon error, it only requires 1/epsilon² samples. And the computational complexity, of course, is exponential in general, but this algorithm is not meant for scalable algorithm anyway. So we just look at small system size and estimate the total error.